Hey everybody, last video for today, and what we're going to talk about now is the Friedel-Crafts acylation. Now, one piece of vocabulary that would help you here is to know what an acyl is. And an acyl is just an older name for a carbonyl. So what the Friedel-Crafts acylation does is it adds carbonyls to the ring. Okay? So here's how the overall reaction looks. You start with benzene. What you do is you react an acid chloride with aluminum trichloride. Now, this is where I normally try to remind you that you can use bromine and iron tribromide too. It might work. I actually don't know, but I will tell you this, that I've never seen anyone do it. So, with the acid chloride, which remember, you make an acid chloride by taking the parent acid and reacting it with thionyl chloride. And you get the acid chloride, and what you make is this. You make the aromatic ketone. So let's see how this works. Remember, the first step in any EAS reaction is making your strong electrophile the chlorine attacks and adds its electrons to the aluminum, and you generate this. I hope this is starting to look a little familiar, because it should be. All right, so now where are we at right here? Here's where we're at right now. So the next step is going to be kind of the weird one, because your oxygen, well, not do that, your oxygen will form a new pi bond and knock that off. So what you've got here now is this. This now is your electrophile. All right, so let's go to the next page and we will look at the rest of the mechanism. There's your electrophile. Pi bond attacks the carbon, which breaks open one of the carbon-oxygen pi bonds, and you are here. Now, do the resonance forms. And I think I repeated myself enough here that you understand that you've got, if I ask for a mechanism, you've got to do the resonance forms. Wonder, can you hear the people thundering around upstairs as I do this? I often wonder sometimes, does Daddy's working mean nothing to these people? And then finally, the base pulls that off. And then there we go. The electrons go down for the E1 elimination, and you have made this, your aromatic ketone. This will work with pretty much any acid chloride you've got in your system. There's a small problem that happens though, and I don't remember if your book talks about it or not. I'm going to show you this in case they do. The problem is the electrons on this carbonyl, the two pairs of electrons on that oxygen, think of the empty orbital on aluminum trichloride as a nummy treat. So what we should probably do is go back to here and say 2 aluminum trichlorides. I did that really fast. Let's look at it one more time. 2 aluminum trichlorides, and then that will put you here. The main reason being with this ketone, this likes to add its electrons, and you end up with just a mess. So, honestly, if you forget the 2 there, that's not going to be the end of the world. Now, this will work for virtually any of the acids out there. As long as you can turn your acid into an acid chloride, this works well. Now, there's one that it will not work. I'm sure there's more than one, but these are the ones that I'm thinking of. So this is formic acid. We've talked about it a few times. It's the primary scent, scent, smell. No, words are hard. It's the primary tracking scent, there it is, that ants produce. So this will convert to the acid chloride, but it is very short-lived. So this cannot do a Friedel-Crafts acylation. It just doesn't happen. All right? Now, why do we care about the Friedel-Crafts acylation? Well, there's something very important that comes out of this. And here's what it is. If you remember from the Friedel-Crafts alkylation video, I showed you that if you take this aromatic ring and you react it with, say, 1-chlorobutane and aluminum trichloride, this would be your product. All right, there's your product mixture. So it looks like this cannot be made. You cannot get 1-phenylbutane out of this, or butylbenzene. Well, you can. You just kind of have to trick your way around it just a little bit. So here's how you do that. What you do, I'm not going to do the mechanism this time because this is mostly a synthesis argument. You take benzene and you react it with that acid chloride and that aluminum trichloride. Yes, I know I said that you need 2 of those, but ladies and gentlemen, like I said, if you mess that up, that's the least of your problems. Now over here, I'm going to write our target molecule, which looks like that. All right? So your product here would be this. Now, is this molecule what you want your target molecule down there in yellow to be? Not yet. It's not yet. But there are ways that we can get there. And here is how. There are 2 reactions that will take this aromatic ketone and go to the alkane. One of them has a name. I think it's like Wolff-Kirchner. I don't care. No, sorry, it's Clemenson reduction. And what you do is you react a zinc and mercury amalgam. Now, you don't see the amalgam nomenclature very often. When you see two metals written next to each other, and one of them is a parenthesis, in the parenthesis, that means it's an amalgam. It is a mixture of the two metals that intermix on the atomic level. Most of the time you mix two metals, they separate out. They don't like each other. Amalgams are a little different. So zinc-mercury amalgam with HCl and heat will turn this ketone into the alkane. How? I've got no fucking idea. I'm not even going to try to fool you on it. I don't know. But another way that works, and I do know this mechanism, I just don't see the need to beat you over the head with it right now, is you mix, whoops, let me do that again. You mix, and I think we talked about this, hydrazine. Write that over here. Hydrazine with potassium hydroxide and I can't remember if you need to heat this one or not, so I'm not going to be too worried about it. Now, the Wolff-Kishner, this is the Wolff-Kishner, it uses hydrazine and KOH to go down to the alkane. Again, the mechanism is known, but you've got enough on your plate right now. I'm not too worried about it. So this is the way we cheat around to get some of these functional groups put together that we normally couldn't. Without the acylation and one of these two reduction methods, we wouldn't be able to put on any carbon in a straight chain longer than 2 on the aromatic ring. All right, so tomorrow we are going to discuss what we can do with nitrobenzene, and then we're going to start talking about what to do when you've got EAS mechanisms, when you've got EAS reactions on an already substituted benzene ring. I know, I'm so excited about it, I could just plots. So, I'm going to leave you with that, and I'll talk to you tomorrow.